Welcome. In this short, we watch the central limit theorem come alive. Idea first, start with any distribution that has a finite variance. Draw many independent samples. Average them. Generate the histogram of the sampling and averaging process. We can see clearly that the average turns bell-shaped as the number of samples averaged increases toward infinity. At the top you see a plot of the histogram of the sample average. The dashed curve in blue is the ideal normal with the same mean and variance. Below, we see that the cumulant generating function of the sample average, as the number of samples increases, moves toward 1/2 times t squared, the fingerprint of a normal distribution. Why this matters in practice? Average several noisy sensor readings on a robot, the result looks more Gaussian. Average polling responses from many people. The estimate stabilizes around a bell-shaped curve. We will show this phenomenon with two examples. Example 1, an exponential continuous random variable with mean 1 strongly skewed to the right. Example 2, a discrete case, Bernoulli coin flips with probability 1/2. In the case of example 1, when we average in copies, the mean stays near 1, and the spread shrinks like 1 over square root of n. Watch the histogram in yellow unskew and settle onto the dashed bell curve. Meanwhile, the curve below bends toward 1/2 t squared. In the case of example 2, each sample is 0 or 1. The sample mean is the fraction of heads. As n grows, the histogram becomes symmetric and tight, while the curve below again into the familiar parabola as n grows. Even though the data are just zeros and ones, the distribution of the average quickly becomes bell-shaped. Difference seeds, whether continuous or discrete, one universal limit. That's the central limit theorem. The theorem is called central because it lies in the core of the theory of probability and statistics. Thanks for watching.